Thanks, Benjamin. Hello, my name is Jay. I'm a senior software engineer and a team lead at Intel. With me is Kate. She's my coworker. And we are going to talk about anomaly detection using Eclipse Kura and Intel's data analytics acceleration library. I'm going to talk about that in the first part, and the next part, Kate is going to do a couple of demos. And some of you might know Scott Lewis. He is also a part of our team. Actually, this anomaly detection is actually a POC. So the main part is we are developing a edge analytics frameworks. That's the main framework that we are developing, and this would be a proof of concept using that framework. To start with, the background. So what is edge analytics? It's as a standard definition of it says, it's an approach where data collection and analytics is done, in which the automated analytical computation is done on the data, either on the sensor or on a switch or any other devices, instead of sending the whole data to centralized location. In the fact that we are converting just a connected device into making it into a intelligent device. So where the decisions could be made right at the place where the data is generated. So why use edge analytics? One is to improve the use case latency, and then to improve the security and the privacy. So instead of sending the whole data to the cloud, you can just aggregate it, or take some decision on that and then send it to the cloud. And also to conserve the bandwidth. Instead of like as I said, you don't have to send the whole data. Only required data could be sent. It's like something buy local, right? You don't want to reduce the footprint, the carbon footprint, something like similar to that. You do it locally, and then when something exotic, you want to use, which is not here, then you go and get it from the cloud, from far. So as I mentioned before, we are developing an edge analytics framework, which is based on the open source softwares like the Kura, and then Intel's DAAL, the data analytics and acceleration library, and OSGI framework. So we are also using Eclipse January for like iDataset and metadata. So the purpose of this framework is to help the developers to ease for developing the analytics applications, so that it is easier for them to concentrate on their logic than the implementation of the application itself. So, and it's Java based, so which is a very popular programming language. And it uses OSGI for dynamic component system for Java. To talk about the framework itself, this is a typical application structure. Here we can create the containers. The containers have some components which are actually basically the OSGI bundles. So the data, the green blocks represent the sensors, and the containers are configured using XML. Using the Kura web admin, the one that you just saw, where the Kura wire canvas was made available. So it's the same web interface we are using to provide the XML, which has all the details for how the pipeline is configured. So to start with, the sensor data is collected and ingested. That's one component, and we are using the event admin, to communicate the data between the components. So they are like producer-consumer kind of components where one processes the data and puts onto the event admin, and the other gets it. So we have data ingestion and data formatting, and then we use the DAAL library to do the machine learning and analytics part of it. And then we have components that does aggregates the results, and it has some rules where it can decide on when an anomaly is detected, can be triggered into the cloud. So the another configuration would be to use the collective information that the cloud has, and then create a model that uses the collective data from different edge devices, and then download the trained model back into the devices, so they are better aware of the learnings from different devices out there. So that's another configuration that we are working towards. And also I would like to mention that the configuration, it's not just one configuration you can have. You can have like multiple sensors going through a single pipeline, or you can have one sensor data going to multiple containers. So it can be one to many and many to one configuration is also possible. So this is the stack. It's pretty basic. We have the embedded Linux at the bottom, and we have the open JDK that is used by the OSGI framework. We are using Equinox 3.11. And then at the top layer, we have Eclipse Kura, and then the framework that we are working on, which uses the DAAL. And you can have customer components. So talking about DAAL, so this is the highly optimized, building blocks for the data analytics, which contains the full sleeves of components used for data analytics, starting from pre-processing, formatting, and analytics, and then modeling, validation, and decision making. These are pretty agnostics to where they are used. I mean, it can be used in a big cloud, so a super powerful cloud, or it could be used on the edge also. And these support batch processing, and then streaming processing, and then distributed processing. So it takes care of all the different modes of how the data is accessed. So it has an Java wrapper. These are basically mainly built on C++, and then it has Python wrappers, and C# and Java. Then
yes.
It can be...
But can you hear me over the speakers? No.
So it can connect to popular databases like SQL, NoSQL, or in-memory. And it can be easily connected to other analytical platforms like Hadoop and Spark. These are highly optimized for Intel architecture. So if you want to use Spark still, but want to use the optimized DAAL libraries, you can actually replace that and use within Spark or Hadoop. So, and by the way, this is open sourced, and open source under license, Apache 2 license. So you can go to that web page and have a look. It's pretty well documented too. Using this platform, we are doing a couple of proof of concepts. So one is with the utility company, and the other one is the manufacturing. So I'm going to briefly talk about these two. So what's the configuration and what we are using for. So the first use case is monitoring of the transformer cooling fans. So this utility company has like lots of transformers spread around, and each transformer has 8 to 12 cooling fans. So what they do right now is to make it efficient, they just replace the fans at a periodic time, like 3 years, they just go replace them. Doesn't matter if they are bad or still working well. So they just want to do it when they go out. So to increase even more efficiently, to use them, we are putting sensors on them, and then capturing the vibration data from those sensors and monitoring that vibration to see to predict when the fan is about to go bad, so that you can send a notification and someone can come and just replace that one fan when it is about to fail. So as you can see, the sensor is on the fan, and we are using monitor sensors to capture the acceleration data, which actually does post FFT data. It sends speed and frequency on all three axes, and over RF frequency, it sends to the hub. And from the hub, we are capturing the data and sending it to the MQTT broker that's running on a gateway. So the gateway is an Intel gateway. It's an Atom-based gateway, a dual-core gateway. So, and from the processor, from the MQTT broker, our framework subscribes to the broker, and the data flows through the pipeline, goes through the analytics, and then the decision making and notification takes care of the rest of the stuff. So this is one use case. So the notification for the POC, we are using Karaf, which has a web server, but it can be connected to any other cloud services using regular protocols. For this purpose, we are using MQTT protocol for the communication. Since it's a lightweight communication, there is no data that's being sent. But we also have plans for sending the data around the notification, or maybe even more data. So the other POC that we are working on is in the manufacturing field, these robots handle, they have the bearings at each of their elbows, and those bearings are the one that are more susceptible to damage, and they replace it. When a robot comes to a repair, they just replace all the bearings. They don't look at if they are bad or still working fine. So we are working on again analyzing the vibrations from the robot arm. In this case, we are using a microstrain sensor, which sends raw acceleration data. So what different we are doing in this is, since we are getting the raw acceleration data, so the pipeline, the analytics framework does the pre-processing. It does FFT, fast Fourier transform, and it extracts the features, like the median frequency, for which would be used for the input as features for the analytics. So the same thing, the analytics runs through that, and it detects anomaly. We use the data strategies like rolling window concepts, and then it counts the anomalies and
check.
determines
This
if it
is
is
221D. Awesome.
if it is worth sending a notification.
Like this?
So I think. So we are using Kura, as we mentioned before. So the part of the Kura that we are using, I've highlighted. So we are using the data services for storing the data. And then we are using MQTT PAHO for communication with the getting the sensor data from the sensor hub. We are using MQTT messaging to send messages to the cloud. And WebAdmin, we are using it for configuration, for the configuration of the pipeline container, which Kate will be showing next. Take over.
That's okay. So as Jay had mentioned, this is what the pipeline kind of looks like for the two examples that I'm going to show you. And kind of going from left to right here, the first thing we have is a user-defined pipeline configuration. So the pipeline itself is just configured using XML that gets inputted into the Kura web UI. And then that XML describes how to put the service component describes to the service component factories how to place the different components into the container. So right now in the POCs that Jay had described, we have a data strategy, an algorithm, and then also a decision/notification. And then those containers get placed into the pipeline, and then the data from the sensors just flow through the pipeline, through the container. So you can dynamically configure any of these pieces however you want. And also, they can be user-defined as long as you code the components to our interfaces. So for instance, if you wanted a container that didn't have any of these components, and you just wanted to write your own custom component, you could do that. And actually, I'll show an example of that. So the two demos I'll show you is the first one, it's going to use vibrational data. And how the pipeline is configured, it's vibrational data from an accelerometer. And how the pipeline is configured is the first piece is a simulator that's going to send the data through the pipeline. And then there's a data converter that will normalize the data. And then a data strategy where we're using the Kura DB service to save off the normal data points. And then after that is an analysis algorithm that will look for the anomalies in the data. And then if there's anomalous data, it will just go ahead and raise a notification. And then if there's time, the second demo that I'll show you is just one where we took our data container and we just have one component in it. And that's just where we're sending the MNES data set through, which is just images of digits. And then we've pre-trained a neural network to recognize the images and then just shoots out the classification of the images. The images are between 0 and 9. So, okay. I think this one. Okay. So what I'll do. So this is an example. The first example I'm just going to show you. Just hold on here. I think we just, yeah. There we go.
Maybe you can see.
Oh, there we go. Okay, great.
You'll have to look there.
Yeah,
Sorry.
that's okay. So here we go. I'll show you. Oh, here we go. So here is the input, the XML, that describes how the pipeline is configured. If you just take a quick look at the XML, so for the first example, we have the FlexAlgo container, which holds the 3 components that we talked about. We have a data strategy, which is the golden copy, which what we saw in the pipeline. And then the algo we're going to be using is the outlier algo, and we have some hyperparameters here we just set. And then the number of anomalies that we're going to detect with the algorithm before it raises a notification. And in this case, it's 2. And then in the second example is the one where we just have the, where we've kind of wrote our own custom container that just holds the neural network that's going to recognize the images. So here I'm going to just click apply. Okay, so the next, what we're going to do now is start sending the, we're going to start sending the vibrational data through the pipeline so that we can start detecting the anomalies. And the first 100 data points it will look at, and the first 100 data points it gets, it will determine that those are normal data points. So after that, anything that has a high z-score, in the case of this outlier algorithm, is going to say it's an anomaly. So now we're sending data through the pipeline. And then we can see if any anomalies come through, just right here. So I'm just going to delete these. These are some old ones. So we have some anomalies. We're probably about at 200 data points. And you can kind of see, here they are. And so in this, I know this looks like a little bit verbose, but really what you're seeing is what pipeline the anomalies are associated with. And you can also change different parameters in the pipeline. So if you're detecting too many anomalies, then you can tune it. So the second example I'll show you is one where we're using the DAAL. And what we've done is we've just created a simple neural network where it's just a 2 hidden layer neural network. And we're going to use it to classify the MNES data. And in this case, all we're doing is just classifying the images. We're not sending any anomaly notifications or anything like that. And we've also used the Intel DAAL libraries to do this. So what you can do is you can train your neural network offline, like let's say in the cloud, and then you can take the weights and biases and push those to the edge device. So here, we're now just getting the images through, and it's telling us the probability of it for each digit. So if we just take a look at one of these, you can see with this one, so it's a 7. So if we scroll over, we would see the highest probability is that it's a 7. And then also inside the framework, you can run these data pipelines side by side. So you can run multiple ones if you'd like. And I'll just show you. Like in this case, we could run both of these examples side by side. So you can see we're running 2 pipelines at the same time. And we do that with our edge devices. So it kind of gives you a way to configure these, the pipelines in the little pieces. That's kind of it. That's the end of the demo.
Any questions for JRCAT?
Yeah.
So as you're running that, so that's a stream of, I guess, water fans, I suppose?
Yeah, like in the PSC that we have, we could run multiple fans through the UTX.
How about the correlation? Because shaft vibration is not necessarily root cause for failure. Say it's Phoenix, it's 150 degrees or 35 degrees, whatever it is, on the rooftops, and it fails because something just melts, the wires melt off or something. Can you have a thermistor in there that's correlating temperature with vibration? And so if you would maybe help me to understand how you would do multiple of that correlation of different data types.
Yeah, so in that case, what you could do is you could have the multiple sensors going into one data pipeline, and then the algorithm might, look at that data using like a Gaussian mixture model or something like that, and determine that the fan is anomaly based on all of these different inputs. Something like that, you would probably want to, the nice thing about the way we've set this up, something like that, you could write your algorithm offline and then just put it into the edge device itself. Yeah.
One last quick question.